Today we are breaking down the LongCat-Flash-Thinking-2601 technical report.
This is from the Meituan LongCat team.
And it's a huge one. We're talking a 560 billion parameter mixture of experts model. It's making a serious claim for, well, state-of-the-art in open source agentic reasoning.
Right. For the really hard stuff, search, complex tool use, coding, the model activates 27 billion parameters for every single token.
But the real story here isn't just the size, it's the whole strategy behind it.
Exactly. It's like a four-pillar approach. First, they synthesized over 10,000 different training environments because the real data just doesn't exist at that scale.
10,000, that's incredible.
Then they built a custom infrastructure, they call it DORA, for asynchronous reinforcement learning. Then, and I love this part, they injected real-world noise, broken tools, ambiguous instructions.
Building the robustness from the ground up.
Exactly. And finally, there's this test time method called heavy thinking mode.
And that's what gets them the headline result, right?
That's the one. It hits 100% on the AME 25 benchmark.
100%. That's the kind of number that makes you double-check the paper.
It is.
Okay, let's back up. This is AI Paper Podcasts, and we're going to tear this report down piece by piece. I want to start with the problem they're trying to solve. They argue there's an agentic gap. What do they mean by that? We have models that are great at math, so why doesn't that just transfer?
It fails because of the feedback loop. I mean, think about it. Solving a math problem is an internal process. It's a closed loop.
Right. You write down the steps, you get an answer.
Exactly. The world doesn't change while you're thinking. But an agent has to interact with a dynamic world. It has to, call a tool, wait for a response.
And that response might be an error message.
It could be an error, a timeout, a giant JSON file it has to parse. The agent has to react to new information at every step.
So it's the difference between solving a physics equation on a whiteboard and, say, actually trying to land a drone in high winds.
That's a perfect analogy. And the core bottleneck is data. We have trillions of tokens of text. We just don't have trillions of tokens of high-quality, long-horizon, error-correcting tool use.
So the LongCat team decided if you can't find it, build it.
They manufactured it. And that's their mid-training strategy. They dedicated, 500 billion tokens just to teach this interaction.
500 billion tokens. That is not just fine-tuning. That's a whole training stage. How are they synthesizing this data? They mention a hybrid data synthesis framework.
So it starts with something called text-driven synthesis. They take unstructured text like tutorials, API docs, instruction manuals, and mine them for procedures.
So it reads, to restart the server, first do this, then do that, and turns it into a list of function calls.
Precisely. It turns the narrative into an explicit check processes, kill daemon, restart server sequence.
But that seems like it could still be brittle. The model might just learn to write kill daemon, but not understand what to do if it gets a permission error.
And that's where part 2 comes in. Environment-grounded synthesis. They don't just generate the text, they actually build lightweight Python environments to verify that the generated code actually runs.
Okay, so it has to work.
It has to work. And they use this technique I found really clever called tool decomposition.
Yep.
They basically play hide and seek with the model. They hide the parameters a tool needs inside the environment. So if the task is delete the temporary file, the model can't just hallucinate delete temp.txt.
It has to look for the file name first.
It has to use a search tool to find the file name, then pass that variable to the delete tool. It forces the model to learn the dependency between gathering information and taking action.
That kills rote memorization. It has to learn the logic.
So,
Search, identify, then execute.
exactly. And they do the same thing with reasoning decomposition.
Yeah.
Instead of just showing the model the one perfect golden path to a solution,
They show it alternatives.
right? They generate multiple possible next steps and teach the model how to evaluate them and pick the best one. So the training data becomes a decision tree, not just a straight line.
This all builds up to what I think is the most impressive part of this paper, the world building. You said 10,000 environments. And these aren't just prompts, they're executable little programs. How on earth do you automate creating a multiverse like that?
It's this automated pipeline. It starts with a high-level domain definition, let's say retail databases.
Okay.
The system then synthesizes what they call a domain graph, a map of all the entities like users, products, orders, and the tools you need. That generates the Python code for all those tools.
But is the code any good?
Well, here's the kicker. Every single tool is unit tested. They have a debugging agent that literally iterates on the code until it passes verification. They claim a 95% success rate on generating these verifiable environments.
So you literally have a machine building the machine that trains the machine.
That's a good way to put it.
But just having environments isn't enough, right? The tasks need to be difficult, otherwise the model plateaus. How do they make sure these 10,000 worlds actually challenge a 560 billion parameter model?
They use a strong solver metric. It's like a video game that gets harder as you get better. They have a strong baseline model, try to solve the tasks. If it finds a solution too easily,
The system levels up.
the system intervenes and makes it harder.
How does it add complexity without just breaking everything?
It merges independent tool chains. So imagine you have an easy task like find a user's address, and another easy task, calculate shipping costs. The system sees the model breezing through these and combines them.
Into find the user's address in order to calculate the shipping cost.
Precisely. It creates a dependency. Now the agent has to coordinate between the user database and the shipping calculator. It's procedurally generating complexity based on the model's own competence.
That sounds incredible for training, but an absolute nightmare for infrastructure. RL is already expensive. Now you've got this massive model that has to wait for a Python script to run in one of 10,000 environments. The GPU must be idle most of the time.
That's the classic environment bottleneck in RL. GPUs are fast, Python is not so fast.
So how did they solve it?
They built DORA, dynamic orchestration for asynchronous rollout. It's a whole system designed specifically to keep those GPUs saturated with work.
Okay, break DORA down for us. What's it doing that a standard setup isn't?
A traditional setup has batch barriers. You send out a batch of, say, 1,000 environments, and you have to wait for all of them to finish before you can do a model update.
It's only as fast as its slowest member.
Exactly. DORA gets rid of that. It's a fully streaming, asynchronous pipeline. Generation, execution, reward calculation, it all happens at the individual sample level. As soon as one trajectory is done, it's sent to the trainer. No waiting.
But wait, if you're updating the model constantly, don't you have a sync problem? Data might be coming in that was generated by an older version of the model. You'd be training on stale data.
That's the staleness problem. It's the biggest risk. DORA manages it with something they call virtual rollout groups. It basically allows older model versions to keep generating data, but within a controlled time window. They accept a little staleness in exchange for huge throughput.
And there's more to it on the hardware side, right? They mentioned PD disaggregation.
Pre-fill decode disaggregation. Yeah, you see it more in serving, but using it for training here is key.
Why is that?
Because in these long agentic tasks, the context is huge. The pre-fill, just processing all that history, is compute intensive. But the decode generating the next token is memory bandwidth bound.
Two different jobs.
Right. If you do them on the same GPU, you get bottlenecks.
Yeah.
DORA physically separates them. Some GPU nodes just do pre-fill, others just do decoding. It's optimizing the hardware for each specific part of the transformer's job.
It's like an assembly line instead of one person building the whole car.
Perfect analogy. And they have this one brilliant hack. They call it CPU swapping.
A hack. I like it.
They're running on accelerators with only 60 gigs of memory, which is incredibly tight for a model this size. When the GPU memory overflows, instead of crashing, it swaps the KV cache blocks to the much slower CPU RAM.
Which is still way faster than recomputing everything from scratch.
Infinitely faster. They claim that all these optimizations make DORA 2 to 4 times faster than a standard synchronous training setup.
So we have the synthetic world, we have the engine to run it. Let's talk about the curriculum. They use dynamic budget allocation, which I assume means not wasting time on easy stuff.
Exactly. Instead of treating all tasks equally, they use a value function based on pass rates. If a task has a 99% pass rate, the model isn't learning anything new.
So throttle the compute for that task.
Right. And if the pass rate is 0%, the model is just flailing, so throttle that too. They focus the compute budget on that sweet spot, the tasks where the model is struggling but making progress.
Now, I want to talk about noise. This is so counterintuitive. Usually you want clean training data, perfect code, perfect instructions. But these guys seem to enjoy breaking things. They inject instruction noise and tool noise. Why?
Because the real world is broken. If you train an agent in a perfect sandbox where APIs are always up and users write perfect prompts, you get a brittle agent. The second it hits a real world problem, it shatters.
So they simulate disaster.
They do. For tool noise, they'll do things like artificially inject a timeout on an API call, or return a partial result like a dropped network packet.
Or just a generic internal server error.
Right. The model has to learn to say, okay, that failed, I should probably retry, or I need to check the status, instead of just hallucinating a good result because that's all it's ever seen.
It's basically training for resilience.
And it works. On their VitaBench noise benchmark, performance shot up from 13.3% to 20.5% just from this noise injection. That's a huge gain in reliability.
Okay, so the model is trained, it's robust. Now we get to inference time. This brings us to heavy thinking mode. How is this different from the standard chain of thought we all know?
Chain of thought is linear. Step A leads to B leads to C. If you make a mistake at step A, the whole thing can go off the rails. Heavy thinking scales compute in two dimensions, width and depth.
Let's break those down. What's width?
Width is parallel reasoning. Instead of one thinker, they spawn multiple thinker instances. It's like asking 5 different experts to solve the same problem in separate rooms. They all explore different paths independently.
So you're more likely that at least one of them finds the right answer.
Exactly. But then there's depth, and this isn't just about making the chain longer.
Right.
Depth involves a summary model. This model acts like a project manager. It looks at the work from all 5 of those experts, aggregates their findings, critiques their logic.
So it's not just picking the best one, it's synthesizing a new, better answer from all of them.
It's an active critique and refinement process, and it can be multi-turn. If the summary model sees a conflict or a gap, it can send them back for another round of thinking. This entire architecture is why they hit that 100% on AMY 25.
But there's no free lunch. All that parallel thinking and summarizing, you're generating a ton of tokens. That must explode your context window.
It creates a massive context burden. Which brings us to their one more thing on the architecture side. Zig-Zag Attention.
Love the name. What is it solving?
It's their answer to the quadratic cost of attention. As the context gets longer, standard attention just gets exponentially more expensive.
So people use sparse attention, but that can create tunnel vision.
Exactly. Sparse attention means a token only looks at a few other tokens so it can miss important long-range dependencies. Zigzag fixes the tunnel vision.
How?
It arranges the sparse patterns in a specific way across the different layers of the model. Think of it like a relay race. Layer 1 connects token A to B, Layer 2 connects B to C, Layer 3 connects C to D.
So even though no single layer connects A all the way to D,
the information still propagates through that zigzag path across the depth of the network. You get the speed of sparse attention, but you effectively recover a global view of the context by the time you reach the final layer.
that's very clever.
And it's critical. They replace about half of their full attention layers with this. It gives them a 1.5x speed up. But more importantly, it's what lets them use Yarn to extrapolate context out to 1 million tokens. You just can't do heavy thinking without that kind of headroom.
Okay, let's zoom out to the scoreboard. We know AMY 25 hit 100%. What else stands out?
Agentic search is a big one. On BrowseConf, they scored 73.1%, which is state-of-the-art for open models. They also built their own benchmark, RW Search, with 200 really complex real-world queries and scored 79.5% there.
And what about for coding? Every developer listening wants to know if it can fix their bugs.
It's very competitive, 82.8% on Live Code Bench, and on SysW Bench Verified, which is sort of the gold standard right now, it hit 80.0%.
80%. That puts an open weights model in the same league as GPT-4o and Gemini 1.5 Pro.
It's trading blows with the top closed models, absolutely.
And that, for me, is the real headline. It feels like this is about the commoditization of top-tier agentic AI. You don't need a trillion users' private data if your synthesis pipeline is good enough.
That's the LongCat recipe, right?
Yeah.
Synthesize a multiverse of worlds, verify everything, inject noise to make it tough, and then use extra compute at inference time to double-check your work.
Yeah.
It's a shift away from just chatbots and toward agentic solvers.
It's a really compelling recipe. But here's the thought I want to leave everyone with. They synthesized 10,000 environments. They automated that process. So what happens when it's 1 million environments or 1 billion? If you force a model to solve puzzle after puzzle involving tools and physics and databases, does it eventually learn the underlying laws of causality just to solve the puzzles more efficiently?
That's the simulation hypothesis for AI, isn't it? At some point, tool use becomes indistinguishable from understanding how the world works. If the environment is rich enough, the agent has to become intelligent to master it.
And we might just be watching the very beginning of that curve. Thanks for listening to this deep dive from AI Paper Podcasts. We'll catch you on the next one.